Hello and welcome to the first of several tutorials in Max MSP to do with neural networks. I've been researching neural networks for my master's course at Plymouth University in the UK, and I came across a lot of information about what neural networks are, how they work, some of the basic principles, and actually how to go about programming them in, say, Python or Java, that kind of thing. But in terms of Max, there didn't seem to actually be that much information. So I thought, well, I'll try and build it myself. And that's what we're going to do today. So I've got this article here, which is how to build a simple neural network in 9 lines of Python code. But it gives us enough information that we can take that, use it for our own purposes in Max, and build a single neuron. Now, if you're watching this, you'll probably have some idea of what a neural network is, so I won't go too much into detail, but essentially it's a load of little clusters of processing known as neurons, and those will take an input, some kind of data, they will analyze it, they will output what they read from that into other interconnected neurons, and eventually a neural network will be able to learn enough about a type of data to be able to get some actual ideas of what it is it's looking at. They're very good for pattern recognition. So say, for example, you feed a neural network 10,000 pictures, half of which have a cat in and half of which don't, and you tell it which ones do and do not have cats in. Over time, the neural network, having analysed all the pixels of each image, will learn what combinations of little clusters of pixels mean cat. And then it will be able to, from a new image that you haven't told whether it has a cat in or not, it will be able to make a pretty good guess as to whether there is a cat there or not. Okay, so that's the basic idea, and as you can probably imagine, there's loads of interesting ways that can be used from a compositional standpoint. So for analysing lots of different tracks of music and then being able to compose its own music in the same style, or taking a lot of the same ideas from that. But for today, we're going to keep it really simple. And I don't actually know too much about how we would get to that stage myself, and I'm using this tutorial as partly as a kind of learning reinforcement task for myself, because I've only just been doing this over the last couple of weeks. So for this individual neuron, what we're going to do is just have this data. So we have 3 inputs and 1 output. And as you can see, we're in binary, so we've only got zeros and ones to keep it nice and simple. And if you spend a minute or two looking at this graph, you will notice that the first input in each of the examples is the same as the output. So that's the trick, that's what we're looking for in this case. The input 1 will always be correct, inputs 2 and 3 will be correct some of the time and not others. Okay, and for us, for humans, that's fairly obvious and doesn't really have any meaning, any use. But for a computer system to be able to see that and recognize it and understand it, that's the groundwork of what a neural network does. And then we'll be able to feed in a new situation, and it will be able to give us either the correct output or something very close to the correct output. It makes a very good guess, essentially. So, first thing we need to do is represent this data within Max. So for that, if we open up a new patch, we're going to use the matrix control object, go into the inspector, make it a 4x4 square because we've got 3 inputs and 1 output and 4 sets of training data. So what we first have, we have 0, 0, 1, 0, 1, 1, 1, 1, 1, 0, 1, 1, and 0, 1, 1, 0. And how we're going to get that data out is we're going to do a message, and then we're going to do get row space $1. So whatever number we send in to this message box, we will be getting that row out of the matrix control. So let's just test this. Hook up a message. It will be coming out of the right outlet. Do 0, enter. There we go. 1, 2, 3. Sorted. So that is our data there. That's nice and lovely. So how does the neural network, or the neuron rather, actually learn from this data? So here is the training process itself, as this guy writes, it takes the inputs from a training set example, adjusts them by a weight. Now, each of these inputs will have some kind of weighting that the neuron will use to determine what its output should be. And it will then calculate the error, so how far off it was, how wrong it was, because we've given it what the output should be, so it can compare that with whatever its output, and that will be the error. And then depending on what direction the error was and how much it was, we will adjust the weights. But we'll only adjust them by a little bit, and then we'll repeat it 10,000 times. So over those 10,000 iterations, the neuron will get to a stage where it's very close to getting the right value every single time, which is exactly what we want. So as it says here, yeah, the weights will reach an optimum for the training set, so it makes a good prediction. Okay, so for the weights, we'll want to have some kind of variable within max that we can keep constant at first and then make small adjustments to. And there's a number of objects that we could use for that in max. There's the value object, for example, that holds a value and then you can recall it at any point you like. But the problem with that is value is a global object, so it will be shared across all your patches that are open at one time. And if we've got multiple neurons in a neural network, we don't want them all sharing the same value. We want them to be individual. So for this, we're going to use the pvar object. And what pvar does is it's a patch-a-local variable which connects to a integer box or a float box. So in this case, we're going to create 3 float boxes, and they're going to be our 3 weights. And just so that we know that they're not regular float boxes, we'll give them all nice snazzy background colours. This one and this one and here. And the way that we actually designate that they're going to be variables is we go into the inspector again, we find scripting name, and we name them. So this one is going to be W1, weight 1, W2, and W3. There we go. So now if we name this pvar W1, what we should see, if I connect a float to the outlet of that, if I change the value here, it changes there as well. And likewise, if we send anything into the pvar object itself, it changes the actual float box there. So that's lovely. So those are our 3 weights, and those can be changed as we go. So initially we want to randomize the weights. We don't want them all just starting at 0, but we want to randomize them within values of between -1 and +1. So how we do that is we'll do random 101, so we get a random number between 0 and 100. We do -50, doing the point because we want it to stay as a float. If you don't specify that it's a float at every step of the way, sometimes Max will change it to an integer, and that can really screw you over. So here what we're doing is, as I say, we get a value between 0 and 100, we minus it by 50, so we've got a value of between -50 and +50, and then we divide it by 50, so we've got between -1 and +1 with 100 different values in between. So that's nice. There we go. So if I bang these, there we go, sorted. Do that a couple of times, yeah, we're getting some negatives. Spot on, that's exactly what we want. Okay, so those are our weights dealt with for now. So the next bit is we want to find a way to deal with this information. So we want our 3 inputs. So the way we're going to do that is when we take out the inputs and the outputs, we want to separate those. So for that we use a lovely object called zl.equals. And if you're not familiar with the ZL objects, you really should be. They are list processing objects of all shapes and sizes. They can do anything under the sun to list objects. If you have a look through the Max Help file, it's got all of them featured here. They are brilliant. If you have a look at some of them, you can work out what they do quite quickly. And you might think initially, oh, well, that seems really cool, but I don't know when I'd ever need that. If you're ever working with lists, you will need it. Remember that they're here. Come and find them. They're great. Okay, so what ZL-Eccles does is it is linked to the ZL-Slice object, so it's literally slice in reverse. And what ZL-Slice does is it takes a list, we'll give this an argument 1, and it slices it at the point that you specify with the argument there. So it will slice it after the first part of the list. So here, if we just test this, connect it up to 2 message boxes. So we get 1 here, and then anything after that over here. If the list was, a million numbers long, we'd get all of them apart from the first one over here. And Eccles simply does that in reverse, so it slices it on the right. So we're going to do ZL-Eccles 1 because we want to separate the right-hand one, which is the output, from the 3 inputs. So put that into there. Lovely. So then once we've got our 3 inputs, we want to separate them and index them so that we can send them all to different places. Easiest way for that is an object called listFunnel. And what listFunnel does is it takes a list and then splits it all into individual messages and indexes them. So it puts a 0 before the first one, a 1 before the second, etc. So here it will take our 3 inputs and it will assign them 0, 1 and 2. And this synergizes really nicely with the spray object, which will give an argument of 3 because it's going to have 3 things coming in. And as if you hover over the outlets, you'll see we get outlet number 0, 1 and 2. So whatever index it reads from the message coming in here, it will send the appropriate number out of there. So that's lovely. So now we'll send those into here. These can be our 3 inlets. Let's move these up here, make it look a little bit nicer, otherwise we're just going to be going down and down and down. And here we go. There. There. And that there. Okay. So we want these inputs to be adjusted by the weight. If we go back to the article, he gives it all here. So the neuron's output, the formula we want, is each of the inputs multiplied by their respective weights and then added together. So we want the sum of all of that. So beneath each of these, we want a times object, again specifying float. And we also want our lovely pvar object with the appropriate weight going into that. So when we get the input in, it will be multiplied by the weight. 1 second, just get that in there. And change this so this is W2 and W3. Okay, so then the next thing we want to do, that will give us a result, but we want to, as he says here, we want to normalize that so it's between 0 and 1 because we're looking for either a 0 or a 1, and depending on which direction it is, we'll know if it gets closer to 0 or closer to 1, we'll know which one it likely is. So he talks about this here, the sigmoid function, which draws a curve based on what the number is. If it's positive, it converges towards positive 1, and if our x value is negative, it converges towards 0. And for various reasons, this is a very useful function for neural networks because the further into either the positive or the negative it gets, the more certain the neuron is that it is either 1 or 0, essentially. But again, I won't go into the detail about that. But the function is 1 over 1 plus e to the power of negative x. And x, in this case, is our weighted inputs, the sum of our weighted inputs here. So we want to do here 1 over 1 plus e to the power of negative that. So we want to make this a negative first of all. We want to add them all together first of all. Now the way spray is going to work is it will work that one, then that one, then that one. So we'll get them in this order. So we want to do 2 plus objects, this one here and this one here. So we'll be getting this one first, goes into there, this 1 second into the hot inlet, so then those two will be added together, the result of which goes into the cold inlet there, to then be added with this. So then coming out of here will be the sum of all of those. We want to then multiply that by -1, so it becomes minus x, as it were, and then we want to do e to the power of whatever this is. So we want to do a trigger object because we want to first send out this float value and then send out a bang. This is probably going to all go down out of the screen anyway. Oh, sod it, let's just leave that where it is. So make a message box, and then our value of e that we're going to use is just to, what, 6 decimal places? Yeah, we're going to do 2.718282. We could do e to more decimal places, but this is perfectly adequate for our purposes. And then we want to do a power object, or pow object. Specify that it's a float again. Put this over here. So we send the float into there, because that's what we're raising e to the power of, and then it will bang this value of e into there, and then we'll get our results out of here. That's lovely. So then we've got that, we want to plus 1 to it, and then we want to do all of that, 1 over all of that. So plus 1, and then exclamation mark divide, because then it will take the whatever you're putting into the first inlet, it will do your argument over that. So 1 divided by whatever this is. So that is our sigmoid function. So now whatever comes out of there will be our value. So if I rebang these weights, so we've got a set number of weights there, we'll send out row 0, enter, and we've got a value of some kind. Great. And that's the value currently when it's been given 001. With these current weights, it thinks the answer is 0.681, which obviously isn't right, because the answer should be 0, but it doesn't know that. We're going to teach it that in a bit. So what we now need to do is, from that output, we then need to adjust the weights. And again, the formula he gives here is we're going to adjust the weights by the error times the input times the sigmoid curve gradient, and that is to do with how sure it is either way on this gradient. And the way we find the sigmoid curve gradient, he talks about it here. You can read the article for yourself if you want to get more information about it, but we need to do the output of the neuron times 1 minus the output. So let's do that. So we want to do, again, let's move all this out of the way. Make it look a lot nicer. That's much easier. Why did I not do that at first? Lovely. Okay, here we go. So we want to do a trigger and 3 Fs actually, and you'll see why in a minute. But then underneath that, we want to do exclamation mark minus 1. So we want to do 1 minus the output, which will be this. And then we need to times it by the output. So this is why we've got the second float here. This float is going to go into the right outlet of there. So we've got our output, so 1 minus the output times the output again, which is here. We then need to times it by the input. Now the input is going to be different for each one, so now we need to split everything up. We need to do another trigger. We need to do trigger FFF. And then send it to 3 multiply objects. And that to there, that to there, that to there. And then we've got, if you remember, these floats over here, these are our inputs. So we also want to send those to the right inlets of each of these multiplication objects, because we are multiplying now by the input each time. tidy these up a bit. Yeah, it's a bit better. Let's move these down a bit. Lovely. Okay, so we've multiplied by 1 minus the output, we've multiplied by the output, we've multiplied by the input. We now need to multiply by the error. And the error we work out by taking the known output here. So let's take that over to a float. If you remember from Eccles, we'll be getting the last digit of the list coming out here. So that goes over to here, which will be the output. Move this down a bit. Okay, and here is what this final f is here, because we need to take the output, compare it to the known output, right? So we'll do a trigger tbf again. We could have probably combined this trigger up with there, but it just makes it easier if we just see what's happening here. We do -0. In fact, we want to get rid of this float. We want to keep it with this instead, because we want the output to first be stored there, and so we can bang it out later. We don't want it to be going through and triggering the calculation early. That's why. There we go. So the float of our incorrect output will be sent over to there, and then it will bang this. So it will then do the correct output minus the incorrect output, which will then give us the error, so how much we're off by. Multiply 0 point again, make 3 of those, send that into here, that into here, and that into here, because this one the error will have been calculated first, so they can go into the cold inlet. Okay. And then the final thing we'll need to do here is adjust the weights by this new amount, because this new amount that we've got out of each of these is the adjustment, and it'll either be a positive or a negative adjustment, but we just need to add it to the existing variables. And the way we'll do that is we'll do tbf. So we're going to trigger the value and then a bang immediately after again. And we want to do pvar w1. Yeah, nice staircase of pvars. Pvar w2 and pvar w3. So we'll have that going into there. No, we won't. I'm being an idiot. In fact, again, let's just bring this all up, because we're just going to run out of space otherwise. Here we go. We make 3 float objects. We want these to store pvar values. And then we want to do plus objects, so that the float, which will from here, which will be our adjustment, goes into the plus. And then the stored f, which is the value of each of the variables, is then banged out into this addition object, the result of which is then sent right back into pvar. And if we do Command Y on that line, you can drag it like that patch cord rather, make it look nice and neat like that, like a little loop. There we go. And that is actually more or less everything. That is the neuron itself. So let's just save this. Neuron basic test, or whatever you want to save it as. The only thing we've got left to do is to make the data be sent out 10,000 times. So for that, we want to create a counter. We want to do counter 3 because we want to be counting from 0 to 3 for this getRow object. Now the thing about max is if you create a kind of loop, which is what we want to do to get it doing it 10,000 times, Max will get very upset and it will think that you're trying to create an infinite loop, and it will go, no, 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 I'm not having that. Then it will freeze your patch and say Stack Overflow, because it thinks, even if you have put in a get out clause for the loop so that it ends early, Max will go, no, I don't like this. You'd given me too much to do, I'm not happy. So the way we get around that is we create a pipe object which will delay a message, and we just do 1, which specifies 1 millisecond to delay it by, and then we send that into there. And that gets around the Stack Overflow, and that will then work. Obviously you don't want to leave something running infinitely because it will slow down your computer, but that does our job for us. So that will now count through each of these 4 rows and send them into the patch one after the other, which is great. It's exactly what we want. So how do we get that to actually be triggered after all of this has happened? We don't want it all just happening at once, because otherwise the patch might not be able to cope with it all. What we want to do is make one final TBF object here, get it from here, because this will be the last one that's done. If you remember, these are triggered in this order, so this will be the last one. Make that look a little bit nicer. Have I done that right? Ah, no, that's fine. So yeah, I'm being an idiot again. Get rid of this patch cable there. Drag them all up a little bit. Then make it here. TBF, because we want the float to go to there, just as it is with the other 2, and the bang will be sent out to ascend here, which we then want to do #0 rebang. The reason we're doing the #0 is, again, if we want this patch to be put in multiple times, we want multiple neurons, and we don't want the send to be a global send, so it sends to all of the neurons, and the #0 will generate a random unique number that will then stay within this patch, so that yeah, that's the easiest way to do it. So once it's done everything here and changed all of their values, it will then send out to this rebang. It will send a bang. So we want to then do a receive #0 rebang. We want to put that into a gate, and then send that into, just so we can see it, let's just make a bang object, put that into the counter. And obviously we want this to go 10,000 times and not 1 time more. So what we actually want, in addition to this, we want a second counter from 1 to 10,000, or we could just do from 0 to 9,999, but this looks a bit nicer. And from the third outlet of counter, which is the carry flag, so as soon as it's done 1 cycle of 0 to 3, it will send out a bang here, and that will count up on this counter. So we can count how many cycles of that it has done. And then when that has got to 10,000, it will send out a bang here, which then send that to a message 0 into the gate. So it closes the gate and the rebang cannot occur and it will stop. Okay, so if I've got that all correct, we should now be in business. So we'll create a big bang that will start everything off for us, and we want to be able to reset the counters each time, so we'll do set 0 into both of those, put underneath this big bang trigger bang bang 1, because we want to make sure that gate is open before anything else. And then bang, set 0, and then bang, the bang. Okay, it doesn't look very nice with all that, but sod it. Let's generate some new values there. And then, if I've got this right, this should now work. Here we go. So you can see that the first value, the first weighting, is going up and up and up. The second and third are going down. The second one not so much, just how to do with how the data has been worked out. It's not completely clear that that's always wrong for some reason. And then we should be seeing any second it will get to the 10,000th iteration, and then the gate should close. Let's see where it's up to. Ah, that's interesting. Why isn't that working? No idea, but for some reason that's not working. 1 second, I'll have a look at that in a sec. Let's turn the gate off. There we go. So that's stopped. What have I done wrong there? No idea. Anyway, we'll deal with that another time. You can work out why that's not working. I can't be bothered. So then let's do a message to test if this is working. So our new case for it to consider is 100. We'll send that into the list funnel, send it in, we get the result of 1. Spot on. And then another one of 0, 1, 1, and we get a result of 0.016. So very, very close. Okay, now this has been a stupidly long tutorial, so I do apologise. But that is the first of the tutorials about neural networks. Next time we'll be going into how to clean this up and abstract it, so make it into a standalone object that you can then copy and paste and specify how many inputs it is, all of that fun stuff. That'll be next time. Thank you very much for watching.